Just when you thought calculus was getting boring, you're about to learn the biggest twist in calculus. Did you know you're about to learn how to undo all that you've learned so far? The biggest secret in calculus is about to be dropped right now. Make sure you stay tuned and be sure to subscribe. Are you ready for the next biggest concept in calculus? This is going to be a game changer for you, and it's the biggest twist in calculus yet. Are you ready? We're going to talk about area under the curve. So we're going to look at this graph and we're going to try to figure out the area under the curve. And by doing that, we're going to draw rectangles because we know how to find the area of a rectangle because that's super easy. But since this line is curved, we'll just draw multiple rectangles to find the area under the curve. So I'm going to start at our point A and draw a straight line up to the function, go over and draw a rectangle down. Then I'm going to start at the point of the function, go over and down, start where the function is, over and down. And I'm going to do this as many times until I get to B. Now ideally you want them the same width at the bottom, okay? So we're just going to estimate that these are the same width. And all we would have to do here is find the area of each of these rectangles and add them up, okay? But now what if we did smaller rectangles? So now let's say instead of going all the way up to this point, we're going to go to this point, or we're going to do about half of that size. And then we go from here and then we go down. And now we're going to take smaller rectangles to find the area. And we're going to add up all of these smaller rectangles. And what do you think will happen to the area under the curve if the rectangles are smaller? Yeah, the more rectangles you have, the smaller the width is of the rectangles, the closer you will actually get. Notice these green rectangles are closer to the function, that pink function, than the black rectangles are. So the more rectangles you put in, the closer they are together, the more accurate to the area under the curve you will get. Hopefully some light bulbs are going off. So hopefully you're thinking, we want as many rectangles in here as we could get to get in closer and closer and closer to the actual area under the curve between these points A and B. And all we have to do is add up those rectangles. So watch how we do that in math. Here's what we're doing. We want to add the area of rectangles. Are you familiar with the Greek symbol in math that means add? If not, it's this funky looking E right here. That means summation. You're going to add up. Now we just have to find the area of a rectangle, which you all know is base times height or length times width, depending on how you want to use it. And in this case, we want to take the height of our rectangle times our width. We just want to add all of those up. So, what is the height of these rectangles? Well, hopefully you see that the height of what we want is the function that we're given. So we're going to sum up, and the height of our function is your f of x, right? Because when you plug in a value for x, you're going to get that y value for your function, and that will give you your height. Now your width is just the tiny changes in the x values for those rectangles. So this is your change in x. If you're not familiar with that triangle symbol, that means change in x. But the thing here is we want lots and lots of rectangles. Do you remember? If we want to get lots and lots of something, or we want to know where something is headed, where it is going, hopefully you're getting light bulbs. So we want the limit as the number of rectangles goes to infinity. Because the more and more rectangles we have, the closer and closer we will get to the actual area under the curve. That's why up here it says area as a limit. We're taking the limit as these rectangles, we have more and more rectangles, we're adding them up, that's that summation, adding up the area, remember this was the area, your height times your width of those rectangles. So now you see where that equation came from. I'm going to show you a couple other notation things that we're going to work on today. This limit and the summation are going to be condensed into a super tall S. This is called an integral symbol, but that's going to stand for our summation. Your f of x stays, and then your change in x is notated as dx. So this is the new notation that we're going to use to show these rectangles, adding them all up, adding up all the area of those rectangles. You ready? Make sure you get this in your notes. We're finding the area under the curve. So the first thing you have there is your new notation. That big S, that summation, it's an integral symbol. Your f of x, which is representing the height of your rectangles, and then the d of x, which is representing the width of those rectangles. And you're adding up all those areas to find that area under the curve. So how do we find these things? And this is where the secret comes in. We reverse the process of derivatives. So all those things you've learned up to calculus right now, those derivatives, we're going to reverse that process. So this process is known as the antiderivative. It is also referred to as integrating or finding an integral. So make sure you have this in your notes to understand all of the language and the notation that is going to be used. So what you need to remember is integration and the antiderivative, those are one and the same, and it means we're finding the opposite of the derivative. So to solve these types of problems, we have to reverse the process in which we found the derivative. So we're going to do a couple problems where we have to think about, if this is my answer, what did I take the derivative of to get here? Kind of like Jeopardy, right? So to find the answers to these problems, we must reverse the process and think about, what did we start with? So let's look at this first one, secant squared x. What did you have to take the derivative of to get secant squared x? Yeah, I'm asking you to pull all that trig stuff. So if you don't remember, make sure you find your notes on trig derivatives. And if you do remember, hopefully you've all said the answer to this would have been tangent x. Okay, let's try this one down here. 3x squared plus 2x. Well, what did you take the derivative of to get 3x squared? So now you have to reverse the process. How does this number get down here when you take a derivative? Comes from the exponent, right? So that means this was x cubed, because if you take the derivative of this x cubed, the 3 would come down front and you would subtract a power. So we have here. So plus, what did we take the derivative of to get 2x? Same thing. That coefficient, that number out front, came from the previous exponent. So it's got to go back. And here's what's great about this process. Once you get an answer, take the derivative, because then you should get what you started with. So it's an easy way to be checking yourself to make sure you have the right answer. Of course, there's a nice easy rule to go along with this, so make sure you get this part down in your notes. This is how a problem is going to be written. It's going to have that summation symbol, your f of x and your d of x. Remember, height, width of your rectangle. To integrate this and get your original function, you're going to take 1 over your exponent plus 1, and then notice in your exponent, you're also adding 1. And then you're going to say, what's this? What's that plus c? This c stands for a constant. Because what happens when you take the derivative of a constant? It's 0. It goes away. However, you have to remember that there could have been a constant in that original problem. So you have to acknowledge, and you just write plus c, that there could have been some constant in that problem. Because of course, coming up, you will have problems where you're solving for that constant. So you have to make sure you have a plus c at the end of your answer. So let's look at this example down here. If I wanted to integrate x to the 6th dx, what do? Well, I'm going to take 1 over, this is my n value, so I'm going to do 6 plus 1 to x 6 plus 1 plus c. Now, of course, you can do this in one step. I'm just showing you. So this would be 1/7 x to the 7th plus c. Now let's check your answer. Go ahead, we're going to check by taking the derivative, right? I'm just going to use dx for my derivative notation. So let's take the derivative of this thing. Well, 1/7 times 7, right? Exponent comes down front. Subtract an exponent. Derivative of a constant goes away. So then you are left with, these cancel, x to the 6th. So that's the basic rule. Now, let's try some practice problems. Doesn't this look fun? All right, so here's what we have. This is your f of x. It's now a lot bigger, right? Well, the rule states that you can take the integral of each of these parts. This is your height. That is your width again. Remember, area of a rectangle. So let's go plug in our rule. I'm going to leave my 3 out front just because it's easier. And then I'm going to do my rule. 1 over, you got to take your exponent plus 1. So 2 plus 1 is 3. X, and I'm going to add 1 to that, 3. Plus, my 5 is going to come down. Now this exponent is just a 1. So we have to add to that 1/2 x squared. Plus, now that 2 doesn't have anything. So technically that is x to the 0 power. So the 2 comes out front. 1 over, add 1 to that, 1, x to the 1st. Plus c, right? Because there could be some constant that we don't know about. So now you can go through and just simplify. Those 3 are going to cancel, x cubed, plus, make that one fraction, 5/2 x squared, plus 2x plus c. And there would be your function. And again, go through, take the derivative of that, make sure you get your original problem. But of course, they're not all going to be that easy. So then you're going to get stuck with something like this and you're going to go, oh, seriously? And you have to pull out some of your old tricks. So the first thing we're going to do is factor that numerator. If you're not solving for the antiderivative yet, you have to keep in that summation symbol. So right now, I'm just factoring that numerator. And your dx must stay there because remember, that's that base, that width of those rectangles. So notice, oh, how lovely is this? Those are going to cancel. Score. Now you're taking the integral of x plus 3 dx. Now we just have to integrate this. So the rule states when we integrate, this is x to the 1st, you're going to add 1 to the denominator, add an exponent. This is 3. Remember, this is x to the 0, so x to the 1st plus c. Not too bad, right? Then you get problems like this and you're like, what am I doing? So you have a couple of options here on how you want to look at this. I'm going to separate the fractions. It makes it easier. So I'm going to rewrite our integral and I'm going to write x to the 5th over x squared plus 3x squared over x squared dx. Now, some people call this manipulation. Yeah, basically. So there's going to be a lot of problems that you're going to have to first manipulate how they look to make them easier to solve. So now all I have to do is go through and simplify each of these fractions. So this becomes the integral of x cubed, right? You subtract your exponents, plus these ones just go ahead and cancel out, of dx. Now you can go ahead and use your integration rules. So now we'll have 1 over, you add 1 to that exponent, plus 3x plus c. Remember your plus c. It's got to be there. You knew this was coming, didn't you? There's always trig to do. But again, in this one, you're going to have to manipulate it a little bit. So sine is squared on the bottom. So I'm going to pull that apart and write two fractions. I'm going to write this as the integral of cosine x over sine x times 1 over sine x. I'm just using some multiplication and pulling it apart because hopefully you'll see that this, what is cosine x over sine x? Yep. Cotangent x. And what is 1 over sine x? Cosecant x. dx. Make sure your dx is in there. Now you have to ask yourself, what did I take the derivative of to get cosecant x, cotangent x? Yep, go pull out your trig notes if you don't remember. Hopefully they were on a nice colored sheet so you can easily pull them out and look at it. Do you remember what it is? Hopefully when you went to your notes, you realized that actually it was negative cotangent x, cosecant x, right? So that means you're just gonna have to make your answer negative to give it the opposite. So it was negative cosecant x plus c. Because if you take the derivative of cosecant x, you actually got negative cotangent cosecant x. So to flip those, you got to make this guy negative, because the negative and then his derivative negative will give you a positive in here. And if you followed that, extra bonus points. So this one again, I'm going to write as 3 separate fractions. The integral of x to the 5th over x to the 4th minus 2x squared over x to the 4th minus 1 over x to the 4th dx. So now we have the integral, and this one works out nice. We just end up with an x, subtract the exponent of an x. Minus this one, however, you're going to have 2 over x squared minus 1 over x to the 4th dx. You're like, great, now I have 2 fractions. How do you get a variable that's in the denominator of a fraction to jump up top? Do you remember? That little negative sign says, hey you, flip over. So if we make those variables in the denominator of a fraction up top, we can make them negative. So watch. So now we have the integral of x minus 2x to the negative 2nd minus x to the negative 4th dx. Now we can go through and just use our antiderivative or our integration rule here. So when you add 1 to this exponent, you're going to get to the 2nd, so we put it here. Now this one. The minus comes down. I'm going to leave my 2. You have to add a 1 to negative 2. So first I'm going to do this piece. If I add 1 to this guy, I'm left with negative 1, which means 1 over negative 1, right, for our rule there, okay? Minus, okay, now I want to take this guy and I want to add 1. I'm going to do this, set this part up first, okay? So if I add 1 to negative 4, you get negative 3, so this is going to be negative 3. I'll go through and clean this up, but for me it's easier to write it out step by step and then go through. So we have 1/2 x squared, negative, negative, positive, 2x to the negative first. Negative, negative gives me another positive. 1/3 x to the negative 3. Depending on how your teacher wants your answer or the back of the book, you could possibly leave it like that. If you want to get rid of negative exponents, it would be 1/2 x squared plus 2 over x. Remember that negative says, hey you, flip over. Plus 1 over 3x cubed. What did I forget? This whole time, what did I forget? See, this is a big no-no. Plus c, plus c, plus c. It has got to be there. See how easy it is to forget it? I would have students write plus c on the top of their quiz so they wouldn't forget to put it in. I know this is going to be a hard thing to remember. You've got to figure out a way to help you remember to add that plus c. Time for more trig. Aren't you excited? The only nice thing about this one is it's not a fraction and these are straightforward trig problems. So the first thing is you can keep that 4 right there with you. What did you take the derivative of to get sine x? Do you remember? It is negative cosine x. And the reason is because the derivative of cosine is negative sine, right? So since this guy's positive, we had to make him negative to make those two negatives drop. Plus 2. So what did you take the derivative of to get cosine x? Yep, it's just sine x plus c. So I'm just going to rewrite this to make this negative 4 cosine x plus 2 sine x plus c. And then you're good to go. That one was pretty easy. Then you're going to get problems like this. And here's the hard part. You cannot just integrate one parenthesis at a time. You're going to have to factor this thing out. So the integral, remember this has to stay there if you're not integrating yet. And now we're just going to factor 2 times 1, negative x plus 2x squared minus x cubed dx. So now we can go through and just integrate each part. This 2 is really x to the 0, remember? So the 2 comes down, then you have 1 over 1, x to the first, minus, this guy is x to the first, 1/2 x squared, plus, this 2 comes down first. Now I'm going to add 1 to that exponent, minus, and add 1 to this x cubed, so that becomes x to the 4th, plus c. Even the best of us forget that sometimes. Okay, now let's go through and simplify. 2x minus 1/2 x squared plus 2/3 x cubed minus 1/4 x to the 4th plus c. Not too much to simplify there. However, some textbooks or some teachers may want you to put it in order of your highest exponent first, so just something to pay attention to. So you just learned the biggest twist to calculus. It's undoing the derivative. It's called the antiderivative. It's called integrating or integration. Hopefully this helped explain it a little bit better. If you have any comments or questions, please do so in the comments. Any topics you want me to cover, I would love to hear from you. Please be sure to subscribe and share this video with another calculus friend. Doesn't this look fun? Oh, seriously? Not too bad, right?